have that touch.
Okay.
I think that this has a touch. Can you see that? Oh yeah, you can do it on this side or that. You did it.
We're good.
I think we're good.
Alright. So my project was on transformations and how they affect like our ANOVA tests and everything. And so a little bit about ANOVA. It's the most common technique for comparing means of different groups in a data set. And it's called ANOVA, which stands for the analysis of variance. It has three assumptions. One is normality of the data. The next one is independence within and out of groups. And the third is the equality of variances. So I did two data sets. The first one was a genome data set, which was on a different group of like crustaceans. And so it was based off the genome size in several of the larger groups of crustaceans found in the ocean. The collector of the data used a random number generator to randomly choose a different species from each of the things of the crustacean, like the genomes. And the species looked at are amphipods, barnacles, brachiopods, I'm going to mess up these names, copepods, decapods, isopods, and ostracods. And that's just a picture of a really cute amphipod, I think. So this is just kind of like what the data set looked like, the like first 5 entries for each one. And then here's just a list of the standard deviations in each of the groups. So as you can see, it's really not like too similar as like amphipods, standard deviation between them was 20.40, and then in barnacles it was only 0.67. So there's definitely like a variance within the standard deviations. And then this is a box plot of the measurement versus the genome, and it's really not clear because of just how like centered some of the data is. So then I decided to take the square root of the measurement and try to plot it, and it was a little bit better, but still kind of congested in some of the plots. So then I looked at the log of the measurements, and a lot of them were a little bit better. The second one to the left, the barnacles, was still kind of congested, but it still like cleared up a little bit. And then looking at the histogram, if you look at just the histogram of the measurements between the groups, it's very skewed to the right as you have a very, very long tail in it. And as we took like the square root and the log, it got more and more normal. As you can tell, that one's still a little bit skewed, but the log of the measurement looked pretty normal to me. And then going through the different ANOVA results, this is just on the measurement. We had an F value of 2.96 and a P value of 0.01, so it's still less than the 0.05 level, so it failed. And then that's just like the squared means, the sum squared, everything. And then as we go to the square root, the F value went to a 5.47 and the P value got even lower. And the sum of squares and the mean squared dropped dramatically from this one to this one. And then the log, which was the more normal of the data sets, you can see that the p-value went even lower, down to 2.93 e to the negative 9. And the f-value was up even more to 11.72. And the sum of squares and the mean square also deviated a little bit more. So like conclusions from the genome data set was that even though all three failed the null hypothesis under the 0.05 level test, there were differences between the tests. Each of the values is much greater than those values in the two tests if you took the regular measurement versus the square root and the log. And if you looked at the histograms, you could see like as the log measurement is much more normal than the other two, and the square root was a little bit closer, but not too normal. And then the second data set that I looked at was muscle shell measurement, and it was looking at the anterior adductor muscle in the muscles. And it took a group of them from 5 different locations, the first one being Tillamook, Oregon, second Newport, Oregon, then Petersburg, Alaska, Magadan, Russia, and Varmine, Finland. And this again, it's just like a little head of the data set so you guys can see what the data looked like. They did standardize the values by a certain coefficient, but I wasn't totally sure what they standardized them by, so it's not the actual measurements. And then these are the standard deviations, and as you can tell, they're a little bit closer together than the genome data set. The Petersburg size is still double that, or standard deviation is double that of the Newport standard deviation, but all in all, it seems to be much closer together. So this is just like the box plots again. It was much clearer, the box plots of this one, than the last one. So you can definitely tell that there's 2 that seem to be higher in the box plots, and then 3 that are kind of at the lower level for all 3. And then looking at the histograms, it's kind of like bimodal with no transformation on it. And then as you go to log, it kind of looks like a mess it's still like bimodal, but there's a bigger range on them. And then taking the square root, it looked a little bit more normal again. So I use square root as being the most normal of the 3 transformations this time. And so going over the results, we got a F value of 7.1 for the normal measurements and a P value of 0.002. And then with the log, the F value went down a little bit to 6.5, and the P value was 0.004. And then for the square root, we had an F value of 6.91 and a P value of 0.003, so it was kind of in between both the log and the regular measurement. And just the conclusions were pretty much the same, that all 3 still failed under the 0.05 level. But by using transformations, we were able to make our data more normally distributed, which created a stronger result. That's it.
Great, thank you. Any questions about? So how about the sum of squares changing? Right, the sum of squares changed.
It got lower in each case. So like if we went up to the genome one, the sum of squares was well over 2,000.
Mm-hmm.
And then with the square root measurement, it was much lower. It was 59, and then the log was kind of in between with the 73-ish.
Mm-hmm.
And same with the mean square, where it was at 340 when we were in the regular measurement, and went down to 9.9 and back up to 11.2.
Mm-hmm.
So it looked like the log kind of split the 2. And then
So just thinking a little about the, what is the formula for sum of squares, right? The sum of the yi minus y bars squared. So it's on the scale of the measurements, right? So if you're on the original scale, it's spread out. Or the square root, it's shrunk in. Logs, it's shrunk in. So the sum of squares will keep changing, right?
Yeah.
And then mean squares are going to be sum of squares divided by degrees of freedom. So if you shrink the y's, then the sum of squares are going to go down, mean squares go down. But it's that F ratio that could become bigger, even though the y's are shrinking in range, because it reflects kind of relative variability. And so kind of interesting to see how it goes. So this wasn't something that we talked about, but what I would find interesting now to ask is, do any pairwise comparisons change once you do the transformations, right? So there's 2 groups in the shells. There's kind of two of them that were bigger and some others that were smaller. Did that pairwise comparison p-value change through the transformations? That would be the thing that I would think about going on next to see how it goes. But any questions? So Dan, I'll put the presentation on the website under today's class, and Dan has provided some code, so if you want to look at some of that, then you can do that. So, good, great, thank you. Good. So. So I haven't put together something for a suggestion for the fourth one, does anybody remember who's fourth on the schedule? I'll look back and do that, but hopefully get it together today or tomorrow and send it around. And then the next presentation could be in the context of whatever we're doing. It's getting close also to a time to give you a first project where you would take a data set that you're interested in, that you're from another class, or that we find through other sources to look at in using one or more of the methods. So, you know, if it ends up being comparing groups, then analysis of variance could be done. We will be going through some things in regression. So it could be more of a regression if there's a continuous quantitative X predictor instead of groups. So that's over the course of a few, 3 weeks or something like that. So there's a little bit of time. So we try to talk about it on Friday to kind of set that out along with a fourth student kind of presentation to go along with things that we're doing. So, but today, for the rest, we're going to move on to chapters 7 and 8. Let me just, one other thing to add, that I'll post another homework that I'll do a little bit more with ANOVA, random effects, comparing groups, to investigate that a little bit more. So. But we're going to talk about simple linear regression, and then we'll get into multiple regression and tie it back to ANOVA. Some of you have had a class in linear regression, so this kind of review, some of you have not. So we're going to present things, we go over formulas, maybe not as much in detail as some parts of the 351 class, but it builds up with additional examples, so hopefully you get something out of seeing different contexts of regression, different uses of regression, and so on. Right? There we are. So the chapter, it's really chapters 7 and 8. And so in this one, it's called simple linear regression. The simple part comes from, we're just going to have one predictor variable rather than possibly several. Multiple regression. It could have been called single regression instead of simple regression. There's nothing wrong with it that it's simple. Sometimes you have a primary outcome, a primary predictor you want to study. So y is going to be our outcome variable. Sometimes it's called a response. In things, particularly in experimental settings, it could be called a dependent variable. Then there's x, which is going to be explanatory. Right? Or something called the predictor variable. Or in an experimental setting where you can change the levels of your inputs, it could be called the independent variable. And I is going to index our subjects or our cases. Subjects or cases or units that we're experimenting on. And so for each one, we observed an x and y pair for each one. Right? So we have n observations on these 10 pairs. And what we're going to ask as a question, what's the regression question? Right? How does the average value of y change as you change x's? Right? Is there, what's the form of the relationship? How strong is the relationship? What can you do in terms of predicting new values of y or average y's from the x's? Right? So how does the average value of y change with levels of x, levels or values of x? So with just the two variables, primarily we start looking at it, right? And see what the pattern generally looks like. And So the best tool for that, we'll have a scatter plot where there's the x's and y's, and each xi, yi pair ends up giving us, an x and a y value, gives us a point on there. And if we have a bunch of those points for different y's, they kind of give this little, scatter up there. And we can qualitatively say, does it seem to be going up? As x gets bigger, does y get bigger? Does it go down? Does it have some curve pattern? And so on. Right? Does it look kind of strong? Does it look kind of straight? Use all that vocabulary to do that. It's good to look at the distribution of x and y as well, because sometimes we'll be in a situation where one of those two variables is extremely skewed. So if our predictor x is really skewed, and we have almost all of our x's down here and a couple x's out here, well, that's going to have a big impact on what our graph can possibly look like. Maybe there's a bunch of, the xi, yi's in this point are kind of in this little cluster here, something like that. But critically, when x is really skewed, then where do these 3 points, their y values, is going to impact greatly our impression of that line. So we might do something like y versus, we might transform x first so that we don't have such a wide range here, and the x's are, they're going to still be kind of clustered, but those 3 on the log scale aren't going to be sticking out quite as far. So you kind of think about what is x and y, and are there big outliers in one direction or another that could affect things before. But we want to, we're going to have a model for that relationship. All right, our model is going to be a linear model, so a straight line relationship between these. Right? So the model that thought about this is linear. Y equals beta 0 plus beta 1x, where beta 0 is the intercept, and beta 1 is the slope. Right. So it suggests if beta 1 is greater than 0, it would be a positive slope between x and y. And there's some, if this is the 0 value of x, then there's an intercept in here, and then the slope is rise over run. So if you go 1 unit at x, that's how much you would expect that to go up. In some cases, the units between x and y can be vastly different. And so you can come up with, betas, like slopes here that would be really, really tiny decimals. Sometimes it's better to transform something to, if something's expressed in inches, well, maybe expressing it in feet would make it, if you can make the units of x and y similar, sometimes it works out better that the slope is on something that's not such a small decimal. Sometimes changing x by 1 is not so important. Right? If the range of x is in the thousands, changing by 1 is not so such a really big deal. But maybe changing x by 100. Right? If you change x by 100, then this would be, the rise would be beta 1 times 100. So sometimes interpreting the coefficients and that slope it makes more sense in a context if it's multiplied by 100, right? So, but our data points aren't all going to be on the line. They're off the line with some variability. And so we add that variability in here by adding a random vector. We consider the xi's as fixed. Right? Fixed numbers. You might say that we condition on them, or we observe them, but then we're not going to look at them as random variables. Right? The EI's are random error terms. And they're going to be distributed randomly as normal random variables with mean 0 and variance sigma squared in the standard model. And this is an I. And we're going to assume in the standard model that these things are independent of one another. So that would preclude some types of data from fitting this model, right? If you have weather or atmosphere or other environmental things with a time structure, a seasonal structure, one day follows the next, and if they're related, then the errors are not really random, but there's a structure that you would do with time series. In many applications, variances are not realistically constant, but in regression, you can do some modifications to deal with that, but we're just going to work with this basic model to work some things out. Often variances are depending on the size of the observation, so X might be related to that. Eventually you can put that into modeling to adjust the model so it is related to that. Right? But under this model, we can look at the average value of Y. Right? The book uses this notation. So mu of Y sub I given XY is, in other notations, this would be an expectation of Yi given the value of Xi, or conditional on it. And it's going to be the beta 0 plus beta 1 Xi. The expectation of that random error is 0, so it's not there. You can have the variance of Y about the regression line. So this would be the variance of Y sub I, it's squares, I'll make it, given the Xi's. Is also sigma squared. So at a particular point of the regression line, the variability is constant there. This could also be written as the variance of the random term. Right, so in the model, beta 0 and beta 1 are parameters. Write that down. So they don't have randomness to them. We don't know what they are, but we don't think about them as random. And the Xi's we don't think about as random, even if we from a random sample condition on them or take them as fixed values. And so the variance about the regression line comes from that random error. And so we can kind of picture that model, if you will. So if this is our regression line, beta 0 plus beta 1 x, at a particular value of x of I here, we get an average response right at the height of the line. So this would be beta 0 plus beta 1, little xi there. And then our errors are added to that vertically. Right? So our errors are plus or minus some distance along there. But where do they go? They're most likely to be close to the line here, with maybe some possibility of being away. And the kind of relative chances of being close, plus or minus, comes from a normal distribution. Right? So there's some normal up here. Right, so this is kind of going out in another dimension. And there's a little normal curve over here. That's the one that's harder for me to draw. Right? So that's a sampling of the errors. If you did a random error, you would draw from this curve. Like, do 3 dimensions, it would be, eventually these screens will be 3D, so to do that, right? And so, given a set of data, x and y, sampling, if you have a bunch of particular values of x, it's going to apply that the data points are going to be kind of around the line with some plus or minus errors, and kind of concentrated around the line with some variance, depending on how big sigma is, right? And that's the model that we're doing, right? So given data, we want to estimate the parameters. But any questions? Some of this is review, whether you've had, this is an introductory statistics course, has covered some of this model with correlation. Yeah, look at the small line over here again. So an estimation, based on our data, we're going to estimate the average response of y through estimates of our linear regression parameters. So the fitted value for case I the book's notation usually is set out to be y hat with a little I on it. It's an estimate also at the mean of the mean at x of I. It is just the value of the estimated intercept, estimated slope, times xi. Right? The error that we have is a residual for case I is going to be our actual y value, the actual value that we've observed, minus our fit value. So y sub I minus our yr hat, like I would usually write it, where the yi hat is of course our predicted. And if this is x and y, we can picture that, right? So if this is our estimated line, well, estimated line doesn't even have to have a little I on it, it's just the equation there. And if we have a particular xi here, then mapping up to here and over is our predicted value, our yi hat. Or equivalently, the mu hat, the estimated average at that value. Our actual data point, though, is going to be someplace. And that distance here is the residual, which is often EI. EI should mean error. Let's call it residual. Right? So we get that distance. Right? And across many different values of our data, we're going to estimate some regression line, the y hat line, and if we have a number of data points around, right, each one then is going to have these residual lines in the vertical direction, kind of like strings pulling on this. Let me draw them all in here, right? And our estimation procedure is going to choose the value of the intercept and slope. If we move it up, some of them get shorter, some of them get smaller, some of them get shorter, some of them get longer. If we tilt it, some of them get shorter, some of them get longer, so we need some balance. So how do we estimate the different things, the different parameters? So how to estimate the things that we need to know, the intercept, the slope. We're also going to estimate this variance, right? Just like in our analysis of variance models, or just two-sample t-tests, we have that underlying variance in the measurements, and if we have that, then we can use it in confidence intervals and so on, right? So we're going to adopt a least squares approach. It's also maximum likelihood. For those of you who are taking the 252 or like that, it's the same estimates that we would get in maximum likelihood estimation. But we're going to look at the difference between yi and its place on the line. Okay. We're going to use all of them. But if we simply add them up, right, some will be positive, some are negative. Right? So we'll just look at absolute distance or more conveniently squared distance. Right? And this is called a sum of squares. Right? Or maybe sum of squared errors, sum of squared errors for this regression. Right? And so if we get to freely manipulate beta 0 and beta 1, we could choose those to make this as small as possible. Kind of make the ones that make the line in some sense go closest. In our picture, right, we want to choose the line so that the square of all these distances added together ends up being small. Right? So to do that is a calculus problem, right? If this is something called Q, like a criterion, some books call it Q. If we take the partial derivative of that with respect to beta 0 and set it equal to 0, we get one equation. And if we set beta 1, take the other partial, set it equal to 0, we get a second equation. So we end up with two equations in two unknowns. And the solution that we get, the solution to that, solving those two equations will give us the beta 0 hat, beta 1 hat as estimates. So I'll write the formulas on the, maybe I'll get it on, we'll write it on the next page, right? But that's would be the procedure to do it. So beta 1 hat ends up being expressible as the sum of the xi minus x bar, yi minus y bar, over the sum of the xi minus x bars squared. So there's something about how x and y are varying together in the numerator. If x and y tend to be bigger than their averages together, you're going to get a positive contribution up there. If one's positive and one's negative, so that they're kind of off the diagonals, you can get negatives. If it's pretty flat, it should all kind of come out to be near 0, but it is standardized by the sum of squares of the x's in there. If you multiply both of these by 1 over n minus 1 and 1 over n minus 1 there, then the top is the sample covariance between x and y. And then this thing divided by that is the sample variance of the x's. So maybe this would be called S of xy over S of x squared. And so covariance over a variance is another way that can be expressed. Right? That's one solution. Then the second one is written in terms of that y bar minus beta 1 hat times x bar. So you calculate this one and then you calculate that one. One consequence of the way how these things come out, that if you have x and y and you have an x bar and a y bar, is that our regression line is going to go through the average there. And so we get our estimates for a couple of things. Right? We can, so what is estimated fit? What is the estimate? Is the estimate of u of y given x at a particular value of this? Well, we're just going to plug in our estimated, or least squared estimated intercept and slope, and put xi into the equation. And that will give us that estimated value there. How about the other parameter? The sigma squared. The formula we're going to use to estimate that is the sum of yi minus yi hat squared over n minus 2. And if we wanted just the standard deviation, we're just going to take the square root of that one. So we calculate the beta hat, beta 1 hat, beta 0 hat, all the predictions, take all the observed errors. So this is ei squared over n minus 2. Right? The variance describes those errors, the variance of those errors. We use n minus 2 because under the normal regression model, expectation of sigma hat. It's just sigma squared, it's unbiased. It also works for distribution theory. Distribution theory for hypothesis tests and confidence intervals. Things work out well when you're doing that one. In term, right, as we'll see, our formulas will use that one. This particular estimate is not actually the maximum likelihood estimator. The maximum likelihood estimator would actually divide by n, so it would say do something else. There wouldn't be anything particularly wrong with doing that in a large sample size. They're not going to be too much different, but it wouldn't quite fit in with the theory, and how things are coded in programs wouldn't be exactly appropriate for that. But in any case. So those are our estimates, right? So what are the sampling distributions of these things, right? How do we get inference for these? Right? We have a number of things we might want to do inference for. We might be interested in the slope. How are things changing? At what rate are things actually changing? We might be interested in the intercept. The book presents kind of an interesting example where the intercept is quite important, right? And if the intercept is 0, it's kind of consistent with the ideas of the Big Bang theory for measuring distances of galaxies and things like that. And so the test of that one is of importance. A lot of other cases, it's mostly about the rate of change. As x changes, how much is y changing? But there's other ones where that's of interest. We could be interested in the sigma squared. Right? We could be interested in the average value of y at a particular value of x. Right? Or we could be interested in a new value of y at when x is some value of x equals x of I. So we can be interested in all those things, and under this regression model, we can get formulas for standard errors and then distributions, so we can do testing. So to do that, we have to know sampling distributions a bit. So it turns out that beta hat 1, when you know sigma squared, ends up having a normal distribution. It's on average, it's beta 1. The expectation of beta 1 hat is the slope that you want, so it's unbiased. Across different random samples under this model, the estimates of beta 1 on average are the right thing. Right? And the variability is related to that sigma squared, but there's xi minus x bar squared in the denominator. So it depends on the number of data points you have. This is a sum I going from 1 to n in there. And it depends on the spread of the x's. Right? Kind of conceptually, if you're trying to understand where a slope is, right, if all the x's are in one spot, you have no way of knowing how things are changing. Right? You can estimate the level at a certain x if everything's one place. But if the x's are spread out, right, then you see the y responses over a long range, and then you can better determine slope. Right? The book writes this one as n minus 1 s of x squared. This denominator over here is that one. So this also says that the variance of the beta 1 hat is this thing. The beta 1 hat is a combination of the y's. It's actually a linear combination of the y's. The y's were normally distributed, and so then beta 1 hat's also normally distributed. There's some algebra to figure that out, and 351 went through that in some detail, but that's the result. Beta 0 hat is is also normally distributed. It's also unbiased. On average, it's the true intercept. And its variance is, there's a 1 over n here, x bar squared over the sum of the xi minus x bar squared. So you know, you estimate the intercept better, you get a smaller variance over here. How do you get a smaller variance? Bigger sample size, bigger range in x's. If the average value of x is centered near 0, you estimate the intercept. The intercept is the value of y when x is 0. So if the average is near 0, you're better off. If x is in the thousands or millions and you're a long way from 0, you're kind of extrapolating, pointing back to 0, so it might not work out so well. And also if the y's are close to the regression line, right? Small sigma means you're close to the regression line, so those things work better. You can say a little bit more about sigma squared as well. The expectation under the model of this thing is sigma squared. And actually the sigma hat squared over sigma squared has a chi-square distribution with n minus 2 degrees of freedom. So that sigma hat squared is a random variable. It has a distribution. In different random samples, you're going to get different values. And the chi-squared is a positive random variable with kind of a long tail. And that's just a distribution result from doing things with the normals. That comes out of there. Often, we want to do inference for these things, so like a confidence interval, and so on. But this standard error formula involves that sigma, right? So we're going to have to do something here to make that work out. So to estimate, estimates of standard error. We're simply going to replace that sigma squared by its estimate, just plug it in. And so our standard error formula for beta 1 hat is going to be our sigma hat times the square root of its that multiplier over there. The standard error that we would use for beta 0 hat is that this one, and then there's a 1 over n plus x bar squared over the sum of xi minus x bar squared, square root of all that, right? But when we replace the sigma by sigma hat, we no longer get normals, right? We're going to use a t-distribution. And because of the structure of this problem, we get to use a t-distribution with n minus 2 degrees of freedom. Why is degrees of freedom in this case n minus 2? Well, we have n observations. And our mean function has 2 parameters, beta 0, beta 1. So we're using up two linear combinations of our y's to get those estimates. Right? So the mean of y given x that we're fitting is beta 0 plus beta 1 x. And so it turns out that there's a minus. Those two get subtracted. But this is related to linear algebra. With endpoints, they kind of span ny values. You could project them in n-dimensional space. Right? And what we're doing in regression is projecting them onto a two-dimensional space. Right, so there's n minus 2 dimensions left, and so there's kind of a geometric interpretation of that. Right, so normals divided by independent, from probability theory, these two things are actually independent of the intercept and slope estimates are not correlated with that variance, actually. It's kind of interesting that it works out. Normality, lack of correlation ends up being independent. So there's kind of some special structure there in the model. And when you divide a normal by a square root of a chi-square, you get a t. So there's some distribution theory. So inference, finally. Inference for beta 0 and beta 1 as our primary inferences. If you take the estimated coefficient minus its actual value, so here j is either 0 or 1, and divide by its standard error, this thing is distributed as a t distribution with n minus 2 degrees of freedom in either case. And so a 95% confidence interval for beta 1 is centered at the estimate plus or minus a t value, the 975 level in minus 2 degrees of freedom, and then the standard error of beta 1 half. Beta 0, same deal. On Friday, we'll look at examples, the standard regression output, estimates and standard errors, and confidence intervals for both intercept and slope. And then we can do a hypothesis test. One hypothesis test, for instance, is the slope equal to 0? Well, really it could be either parameter. It's either the slope or intercept equal to 0. You pick the one you want to think about. In the Big Bang example, it's interested in is the intercept equal to 0. Right? So the t statistic is going to be our estimate, technically minus 0, but that's the null value, over its standard error that we've estimated. And we're going to reject H0. Let's squeeze this in here. If the absolute value of our t statistic is bigger than the 0.975 value of our t reference distribution. So if our t statistic is sufficiently away from 0, right, the center of the t is at 0, the 975 value is up to around 2. Right, so if our estimate is more than a couple standard errors away from 2, or away from 0, sorry, more than a couple, 2.5, 3 standard errors away from 0, we just can't believe that the coefficient is 0 anymore. And we didn't end up rejecting that. There's a couple other things we can do, right? For this, we can do inference for an average. Use of y at x equals some value, call it x of 0. Right? So this is, we imagine that there's a slope over here, and x of 0, we're interested in that for some reason. Okay? And so we're interested in, what is that value? What is that average response on the y? Well, we might want to put in, an estimate and put an interval about that to get some idea of where the average is going. In a designed experiment where you've tried out a bunch of x's and then you choose one, what is your average y value is going to be, right? Or maybe you have interested in a 75th percentile of the x's or some other value to get some idea of what's there. Well, the estimate of this is our beta 0 hat plus beta 1 hat times that x of 0. I'll put just u hat 0 is there. The standard, the variance of that thing of mu 0 hat given the sigma squared is sigma squared, and then there's a 1 over n plus an x of 0 minus x bar squared over the sum of the squared deviations in x. So how accurately we can estimate this point up here, the height of that regression line, right? Depends on how variable the y's are. It depends on the sample size. It depends on how variable the x's are, because if the x's are more variable, we know that slope better, we know the line better. But it also depends on how far x0 is from x bar, right? So if you're predicting on the outsides of your data, right, small changes in the data will cause the line to switch, right? So you can imagine different, if you have different data sets kind of going through and then different lines. Generally, there's a little bit kind of the sampling distribution has a little more variability on the edges, right? Kind of far away from x bar. And that's reflected in that formula. Right? But we can use the same t distribution. So a confidence interval, 95%. Confidence interval for mu sub 0 is going to be the mu sub 0 hat plus and minus our t distribution, and then the standard error. So we're going to put in the estimate of that and the square root of all this other stuff. So we can do inference from that. It's all the same t because of the normality. It's driving all the distributions there and sampling distribution. But that would be for an average response, right? When would that happen? Well, if you're going to do a bunch of cases all at this x sub 0, what's the average you're going to expect, right? But you can also predict for a new case, a new single case. You can do one new order. You're going to have one new school at that level. What's its prediction? So that's called a prediction interval. And so the prediction is the same as the mean. It's best to still predict on the estimated regression line. That's kind of where the average is. But now the variability is more, right? So it takes it's kind of artificial actually how this does. But you imagine that there's going to be variability about the line. What's the extra variability of a new observation? Well, that's a new sigma, a new epsilon, right? What was the and that's added independently. So it's sigma squared plus the variance of the mu hat. Right? So there's a sigma squared. This is from adding epsilon I. I should call it epsilon 0. In the model, it would add it on to beta 0 plus beta 1, x sub 0, right? To produce a new value. And that one is independent error add on with extra variance, so the variance gets added on. So there's a 1, and this thing had 1 over n, and this thing had x of 0 minus x bar squared, and that thing there. So you can do it's not a parameter, it's for a new observation, so it's not called a confidence interval, it's called a prediction interval. And so you would do y hat plus or minus the t-value again times the sigma hat times the square root of that stuff in there. So it's going to be wider for that new observation in there. Now the book does one more thing. We're just about out of time. On Friday, we'll go through the data example and look at the computing for this, and then begin looking at the assumptions again: normality, constant variance. Where do things go haywire for things? Sometimes regression is used, and you want to find an x that produces a certain y. So this one is estimating x. That results in y equal y0 value. Right? Now, if you had the original x and y data, I don't know why you could just run the regression again. You could regress x on y, and then instead of y on x, and then for a particular value of y, you could predict x. You could just switch their roles and run the equations again, right? But then sometimes you've gathered data and it's produced an equation, a regression equation with standard errors and things. And you put that into a paper or document or program, right? And so people only have that. They don't have the original data. Or maybe your data is sensitive to you, if you're willing to publish an equation, but you're not going to hand out people's individual sensitive data. So they can't go back and regress x on y and do it directly. Instead, they are, people have, we want, we're in this regression context, we want the x0 that's going to produce that. If y sub 0, if we have estimated regression, we ultimately want to get this, so x sub 0, if we solve for x sub 0 in this, it's y sub 0 minus beta 0 over beta 1, or if we solve here for a prediction, so this is, we regress y on x to get these coefficients in here. The predicted value of x that's implied by this, if y is fixed at a certain value, right, is that. Graphically, what we're doing, right, is we're going to have x and y, and we have this estimated line from our regression, but now we're interested in y sub 0. Right? So y sub 0 is our interest here. And this inverse thing says map over to here and then map down, and here's our x sub 0 hat. We certainly can do that that calculation and get an x sub 0 hat. Well, what's the standard error of that? What's its sampling distribution? Things are just a little bit more involved, and I'll just give you the answer now. We might go through, or maybe I'll give you a handout on how this works out. But this is a ratio of two random variables. We can't very simply take the expectation or the variance of that. We actually do a Taylor series approximation to it, to do a first order approximation, and figure out the variance and expectation of that thing. So it turns out that the variance of x sub 0 hat from our prediction, so again, x sub 0 hat is our y sub 0 minus beta 0 hat over beta 1 hat. turns out to be the variance of estimating y given at x hat, estimating the average at that point over beta 1, the absolute value of the slope. So this one again was sigma squared. There's 1 over n plus x hat minus x bar squared over the sum of the xi minus x bar squared. It's there over beta 1 in absolute value. So to estimate that, you're going to plug in the sigma hat and the beta 1 hat and do that. Right? So you can do an interval, 95%, in calibration interval for x of 0. Where is that point? The place at calibration, or the other place that I've seen this is when I was teaching the Statistics 220, Introductory Statistics for Scientists and Engineers. The engineering book in the regression chapter had quite a bit of this calibration thing, right? So it's going to be this x of 0 hat plus or minus t value point, 7.5, n minus 2. Then the sigma hat from R, the regression of y on x. Right, the way that we, and then there's a 1 over n plus this x hat 0, I guess, x bar squared over this. This is also sometimes called the sum of the squares x's, and all of that over the absolute value of beta 1 hat, and the square root of all that. So it's a little bit more complicated than a formula, and it's a little more derivation to get to it, but you can do that too. So that's the whirlwind introduction to this kind of estimation of formulas. So it's covered in the book. We'll go over example, and so over the next, couple next week or so, check it out. If you ask questions about it, I'll see you on Friday. And homework. Oh yes, thank you. Oh, okay. Thank you very much. Brings back everything. Connor, did I get your homework?
Oh, geez, thank you.
Yeah. Save you a trip later. Thank you.
Yep.